I guess we'll get started. So in last lecture, I gave you a whistle-stop introduction to computability theory and complexity theory and quantum complexity theory. The only thing you'll need to actually know or have wrapped your head around from the last lecture is the definition of, for the purposes of this lecture, is the definition of the complexity class QMA. So remember that QMA we defined to be was kind of the complexity class that we built up to defining with everything we did last lecture. So these are decision problems, so yes, no problems. And if we've got a problem of size n, then a QMA problem is one where there exists some poly-sized quantum circuit, so a quantum circuit with polynomial number of gates. Now I'm going to say the number of gates is t, which is some polynomial in the problem size. And this verifier circuit should be able to check, for yes answers, it should check Merlin's witness and output 1, accept the witness with high probability if the answer indeed is yes, and conversely, if the answer is no, then there should be no way that Merlin can supply a witness that tricks Arthur into thinking the answer is yes. That should happen with low probability. So last lecture we had these I had these probabilities as 2/3, 1/3. I'm now going to take advantage of the fact that I mentioned but didn't prove that you can actually amplify these probabilities. The 2/3, 1/3 are arbitrary. We can amplify them to something close to 1 and 0. So 1 over poly close to 1 and 0 without changing the complexity class. So this is the same class of problems as before. So I'm going to now fold that into the definition of QMA. Good. And in case you're not familiar with this big O, you probably are more or less familiar with, but let's just refresh your memories. So by big O, I mean the rigorous, the precise meaning, not I'm dropping some high order terms from a Taylor series and hoping they don't get too big. Big F, big O of G means that for sufficiently large arguments, so for sufficiently large n, F is upper bounded by G times a constant. And this big omega, which I'm going to crop up a number of times, which may not be so familiar, is the same thing but with the inequality the other way around. So this says F is asymptotically upper bounded by G. This is F is asymptotically lower bounded by G, and we see both are cropping up in the definition of QMA. Good. So in this lecture, I could go on talking about complexity classes. I could probably manage another 10 complexity classes this lecture, maybe another 20 the lecture afterwards, and tell you about the relations between them and do pure complexity theory. And it will be very interesting. There's lots of nice results. It will persuade you about the fact that it's not everything in complexity theory is open questions. There are some actual theorems. But instead of doing that, I'm not going to do that. I'm going to divert to still within complexity theory, but I'm going to divert to looking at instead I'm going to choose to see what we can use complexity theory to say about quantum physics. So if there's a title to this lecture, I guess it's complexity in quantum physics. And I will complexity in quantum physics. And so I hope, with this lecture this is a very important and interesting result that we're going to prove one result this lecture. It's a very important one in quantum complexity theory. And hopefully this will persuade you that complexity theory is not just some abstract definitions and relations between classes, but actually has relevance to physics as well. So that's where we're going this lecture. So what we're going to talk about in this lecture are local Hamiltonians. I'm going to problems to do with Hamiltonians, local Hamiltonians. So what do I mean by a local Hamiltonian? So we're on the same page. So here's a cartoon of a local Hamiltonian. I have a bunch of Cubitt, so Hilbert space C to the D, or if you prefer, these are finite dimensional spins. So my overall Hilbert space is, we're dealing with systems that have some finite number of particles, n. So these are a system of n qubits. Actually, for most of this lecture, d is going to be 2, so this is going to be n qubits. And then, what's the local part? This is worth emphasizing because it can be a bit confusing. There's a bit of confusion between the computer science terminology and the physics terminology. So a local interaction so a local interaction Hamiltonian. So interactions between my systems are, as you well know, described by emission matrices. So a local interaction is one that has the form HS on some, where S is some subset of my system. So S is some subset of the numbers of the 1 through n. So some subset of the qubits, and it acts as identity on the rest. Okay, so we say that H acts non-trivially only on S. Yeah. Okay. And we say that the interaction is k-local if H is k-local if the size of S is equal to k. So if this Hamiltonian acts non-trivially only on k particles. Okay, and we'll often write, we'll use the usual dropping these tensor identities all the time is a bit of a pain. So we'll often just write H sub S, and implicitly the subscript is the particles that this acts on, and then its tensor identity on the rest of the system. So I have an operator on the entire Hilbert space. Okay, standard condensed, you're used to this from condensed matter physics, and it's a fairly universal convention. Okay, so then what the objects of study for all of this lecture are k-local Hamiltonians. So what's a k-local Hamiltonian? K-local Hamiltonian is a Hamiltonian made up of k-local terms. That's right. And it's k-local. So the whole Hamiltonian rather than a single interaction we call k-local if each H sub I is k primed local for some k primed less than or equal to k. So all of the interactions of my Hamiltonian act on at most k particles. So this is a 3-local Hamiltonian that I've drawn here. If these purple blobs are the interactions, so I have some 1 qubit interactions, some 2 qubit interactions, and some 3 qubit interactions. 3 is the maximum. Okay. Okay. So what's the confusion terminology? It's this k-local terminology. This comes from computer science, and it's a bit unfortunate because these interactions, although what I've drawn here looks like they're between nearby particles, there's nothing in this that says that these have to be local in any kind of spatial sense. Okay. It just says, so in physics we would call these k-body. But unfortunately, we're kind of stuck with the k-local terminology now in quantum information because that's it came from computer science, and we're a bit stuck with it now. Okay, so every time I say k-local, think k-body. Good.
So there is no nearby or distant particles?
There is no notion of particles being close to each other or far apart. They're just a bunch of qubits, and small subsets of them interact. Okay, but it could be that a 2-local interaction could interact one thing right at the end of a chain with something right at the other end. Okay. No notion of geometric locality, not for this lecture, at least. And for what people typically, when you see k-local a k-local Hamiltonian in quantum information literature, means what I just said here. If there's some underlying geometry, then you specify that as well. Okay, so I think I don't need to motivate why we're interested in k-local Hamiltonians. These are a good approximation to the kinds of low energy effective models that arise in condensed matter physics. Even though in nature fundamentally interactions are not strictly local, the Coulomb interaction is something decaying polynomially with distance, but in condensed matter systems, shielding, etc., the effective low energy model is well approximated by something that's strictly local. Yes. Well, yeah, that's true. No, that's true. Indeed. No, that's that's a good point. Good. Okay. So, what's the first thing that we might want to understand about when we have such a Hamiltonian? One of the first things we might want to understand about it is the ground state, and even more simply than that, before we can understand the ground state itself, since maybe the first thing we want to know about Hamiltonians is often what the ground state energy is, which, then through that to get a handle on what the ground state looks like. So we would like, if you keep in mind last lecture, we would like to, what I want to do with this lecture is to look at the problem of trying to estimate ground state energies of many body quantum systems from a computer science perspective. Okay, so thinking back to last lecture, what we need to do is before we can attack it with complexity theory, I need to formulate that problem of estimating ground state energies as a computational problem. Right? So then we can start throwing complexity theory at it and see what we can say using that bundle of tools. And in particular, it would be rather nice if I could formulate it as a decision problem that's equivalent to the actual task of estimating the ground state energy, because a lot of our complexity theory is to do with decision problems and we have more tools at our disposal then. So that's not too difficult. That's what I'm going to do. So this is generally known in the literature as the local Hamiltonian problem. So let's formulate it as a computational problem. So input, we have our input to the problem is a k-local Hamiltonian on, let's put some parameters here. So let's say on n qubits with m local terms, local interactions, let's say local terms. And then the output here, well, we want to make it a decision problem. Let's say we want to output yes if my ground state energy, so I'm going to write lambda 0 h for minimum eigenvalue of h. We're in finite dimensional Hilbert spaces. This is just the minimum eigenvalue of this emission matrix. So the answer should be yes if the ground state energy is lower than some value alpha, and it should be no if the ground state energy is bigger than some value beta. Okay, and where do these alpha and beta come from? So there's one extra ingredient here that we didn't discuss yesterday. I have an extra ingredient in this which is usually referred to as the promise, where I'm promised that the minimum eigenvalue falls into one of these two cases. So either the minimum eigenvalue is less than or equal to alpha or bigger than or equal to beta, and the gap between these two values, beta minus alpha, is lower bounded by 1 over a polynomial in n, the number of qubits. So that's my local Hamiltonian problem, and that's the problem we're going to study this lecture. So a few remarks are in order about this problem. Firstly, so forget the promise for a moment. I'll talk about that in a second. Firstly, I've formulated this as a decision problem, but if I had a magic box or an algorithm that could solve this problem, this would let me, with only polynomial effort, estimate the ground state energy to within 1 over poly precision. I just do the binary search type thing that I talked about with factoring. Right? I just ask, okay, first I pick some alpha and beta and say, okay, does the ground state energy lie above beta or smaller than alpha? If it's smaller than alpha, then I subdivide that range, pick a new alpha and beta, ask the question again, and so forth. So like that, I can home in efficiently on a 1 over poly approximation to the ground state energy. 1 over poly because of this requirement. I can't take beta minus alpha smaller than 1 over poly. Good. So this captures, in a precise computational sense, the problem of estimating ground state energies. So what about this promise? So I didn't define. You can formally define promise problems, but rather than do that, in a complexity theoretic sense, there's a standard thing in complexity theory. I just didn't talk about them last time. Rather than kind of define formally what a promise problem is, let's just say that think about this as you can think about this in a number of ways, this promise. So one way to think about this promise is that we're only trying to compute a partial function here, right? So in this, if the minimum eigenvalue happens to lie between beta and alpha, we just don't care what the answer is. We don't care if the answer is yes or no. Output whatever you like, or run forever, or whatever. It doesn't matter, okay? In terms of the Merlin-Arthur type picture, or if you think about this as a game, then this is a game where you win this game if you output the correct answer, or if the minimum eigenvalue falls in this range. In that case, you just win automatically. That's another way of thinking about it. And where does this promise come from? It looks like, okay, I need to solve the problem of what the minimum eigenvalue is before I can even fulfill this promise. That's not our task. We're given this promise by some deity, and we only have to solve the problem, assuming that this promise is true, right? We don't have to check whether this is true or not. That's not the game here. Okay. Now, as a computational problem, if we were actually going to devise an algorithm for this problem, we would need to worry about, okay, but in reality, how can we know this? I'm not going to do that. What we're going to do in this lecture is prove that this problem is actually hard, QMA hard. Because I'm proving a hardness result, having this promise makes the result stronger, not weaker. If I was giving an algorithm for this problem, the promise would make the result weaker rather than stronger. But this is a hardness result that says even if someone promises that this is definitely holds, I still can't solve the problem. Even if this promise is guaranteed to be true by what, it doesn't matter what means. Okay? So because I'm going to prove hardness results in this lecture, this promise is not a problem, it's actually strengthening our results. Okay. Why do we need this promise? Because our problem is to do with real numbers. We've got a problem that if we were specifying things to infinite precision, all of the questions become undecidable for trivial reasons. You can't even read the input to the problem in finite time because it requires infinite many symbols on a Turing machine. So that's another reason why anytime you have a problem that's over the real numbers, then you have this kind of structure where you promise that you're not near the threshold between the two answers. Another way to do this would be to quantify everything over rational numbers, but that's messy and tedious. Yeah. It's the minimum. Lambda 0 is let me write that here. So lambda 0 of h equals the minimum, that's my notation for the minimum eigenvalue of h. Yeah, or you could do them over rationals. It's very tedious doing that. It's much nicer it's equivalent, but it's much nicer to just put this promise.
Do you assume a particular relation between alpha and beta here?
Only this one. They have to be lower bounded by one.
Beta or less than beta?
No, beta is bigger than alpha.
Beta is big.
Yeah.
Okay.
Otherwise this problem makes no sense. So the picture to have in mind is that here's the spectrum of my Hamiltonian, and I have alpha here, beta here. Promise that the ground state energy is not in here. It's either down here or it's up here. Okay. It's never in that region. Any other questions about this? Because this is now, yeah.
So should promises generally be regarded as restrictions on the input?
Yes. Yeah. Good. Okay, so I haven't said what I haven't pinned down what this input is. So what do I need to input here? I need to input a description of my Hamiltonian. Okay, so let's think about what the size of this problem is. How many symbols would I have to write down on my Turing machine tape to input a description of a K-local Hamiltonian? Well, I have to choose some way of it. So I've got m local terms. I could describe each of those separately, separated by some symbol that just says, okay, this is term 1, term 2. I just put some divider between them, some separator, delimiter. Okay, then now I've got m k by k matrices that I need to write down, okay, to some precision. Each of these acts on Cubitt, so each of these is this is a d to the k by d to the k matrices, so I have m d to the k by d to the k matrices to write down. So I could just write out the elements of all of these matrices, where I may write out each matrix element to some precision. I'm going to sweep under the carpet all issues about the precision to which I write down these matrix elements, because it doesn't matter. You can go through and do that, but the thing is that if I write a number to n decimal places, I have exponential precision in n. So I could go through all of this and put epsilons everywhere, and it wouldn't change anything, and you can just go through the whole proof and add epsilons everywhere to take care of the precision. No one ever does it because the precision is a parameter in this problem that essentially, or in terms of the complexity, is one that it really doesn't depend strongly on. Okay, so that's something I'm sweeping under the rug. Okay, we have n qubits and m local terms, and these are k local, to at most act on k. So at most I've got m choose k different terms. because two terms that act on exactly the same set of qubits, I might as well just add the matrices together and just make that one into one matrix. So that goes as m to the power of, n choose k. So that goes as n to the k. So m is bounded by that. So m is always polynomial in k. I think of k as a constant, say 3 or 5 or something, but this is something that's not changing as I make the number of qubits bigger. And d is a constant. It's just the dimension of my spins or my qubits. So this is, in fact, for most of this lecture, is going to be 2. So in fact, all of the number of parameters in this problem goes as something polynomial. So the number of parameters, or the problem size, we can take the number of qubits as a good stand-in for the problem size, as a good measure of the problem size, because the number of symbols I'd have to write on my tape is a polynomial in the number of qubits in my system here. Okay, so then problem size for this problem we can take to be the number of qubits or qubits, number of particles. Okay, so so that's the local Hamiltonian problem, and the result that I want to try and give you the complete proof of in this lecture, and hopefully then have time to talk about what at the end to talk a bit about what the implications of this complexity theory result are. What physics can we draw out of this result? Is a result that is due to Kitaev from around 2000. And Kitaev's result, Kitaev proved that the local Hamiltonian problem is QMA hard. Actually, QMA complete. And I'm going to write, let me say QMA hard. So that's the theorem that I'm going to now spend the rest of the lecture proving. Okay. So this, but what does this, let's say a bit about what does this mean? So this captured in a precise sense the problem of estimating ground state energies of many body Hamiltonians. And this result says that even if you had a quantum computer, it's very unlikely that you could solve this problem efficiently. Right? QMA is probably not equal to BQP. Right? So it's, and what this result says that this problem of estimating ground state energies of Hamiltonians is at least as hard as every other possible problem in QMA, right? Which means it's very unlikely that we can solve this efficiently on a quantum computer unless BQP is equal to QMA. And in fact, this problem is in QMA as well, so the problem is actually QMA complete. The reason I'm writing QMA hard here is that I'm only going to prove the hardness part, because the hardness part of this result is the more difficult thing to prove. The fact that this problem is in QMA, there are some subtleties, but it's not so difficult to prove, and I'm going to leave that as an exercise. Right? We need a witness that there's a low energy state in the system. Well, Merlin could just supply the ground state, and that's a good witness. And that's roughly the intuition behind why this is in QMA. And then you have to do some work to prove that things actually work out. Okay. So what's the idea of how does this proof go? So remember, what do we need to prove? We need to prove a reduction from any QMA problem to the local Hamiltonian problem. That means we have to construct some algorithm that runs in classical polytime that transforms any QMA problem into the local Hamiltonian problem. And this could include QMA problems that have never been written down before, that no one's written down yet, and no one's thought up. So what do we have to work with if we don't know anything about the problem we're trying to transform and turn into a local Hamiltonian to construct this reduction for? All we have to work with is the definition of QMA. So what does the definition of QMA give us? Well, it gives us a quantum circuit. The only thing we know about QMA problems is that there exists this witness verifier circuit. So that's what we need to use. All we can work with is this computation carried out by the witness verifier. So the idea, which kind of dates back all the way back to Feynman in early 1980s. He wasn't proving QMA hardness results. QMA hadn't been defined yet, but the idea that Kitaev built on and then ran with to prove this result is to encode the evolution of U, so our verifier circuit, in superposition in the ground state. Okay. We just have, I mean, at the end of the day, this is a question, local Hamiltonian problem is a question about the ground state and ground state energy. There's no dynamics here. So how do we encode the dynamics of the computation into this? Well, Feynman's idea was to for different reasons, was to construct, the idea is to encode the entire computation. We can do that in superposition in the ground state. So in a state that looks something like this. So we have this is the state of the computation at time t, state of the qubits in our circuit after the application of little t gates in the circuit model. And this is typically called the clock register. And this just counts, so this just takes states in, well, in this lecture, this is going to take states in c to the t plus 1. So this is not a qubit. These are all qubits. These are just the qubits in our circuit. And psi t is the state of the qubits after you've applied t gates. And this clock register, the clock just takes some basis, which runs from 0 through to some orthogonal basis that runs from 0 through to t. And our clock states just, in this ground state, just tick up from 0 to t. Okay, so in this lecture, so I don't have, at the moment, this is a large Hilbert space, which has to get bigger the longer our circuit runs for. Whereas these are all qubits. And I'm not going to have time to do this in these lectures, but there's a way of fixing this up, which is not particularly difficult compared to what we're going to do. There's a last step that I won't have time to tell you about, but is in the lecture notes that I've posted online, of how you can fix up this and make this actually into qubits. There's one trick, again due to Kitaev, but I won't have time to do that. Okay, so let's just, so psi t, well, let me just write some of this out here. So this is the computational register. And this is C2 tensor n. This is the qubits in my circuit. Psi t is the state after t steps, after t gates, if you like, or steps of our computation if we were working in the Turing machine model. Psi 0 is the input state. Psi capital T is then the output state of our circuit for computation. And the clock states is I've already did this. The clock is in the clock states are just 0, 1 up to T. So it's actually not very difficult to write down Hamiltonian with this state as the. So this is called. I should have said one more thing. So this is often called a. This is often called a history state because it's a state that encodes the history of a computation in superposition. So it's not difficult to write down Hamiltonian that has that as this ground state. Can anyone suggest one? No ideas? I didn't say local. Yeah, exactly. So here's the one. Here's a Hamiltonian that has that as its ground state, as its unique ground state. Trivial. Just the orthogonal, the projector onto the other states. That gives all of the other states an energy of at least 1. Okay, that's not very useful. We want a local Hamiltonian. In some sense, the difficulty of constructing a Hamiltonian with this as the ground state is how to construct a local Hamiltonian with this as a ground state. So let me do that. So here's the Hamiltonian that Kitaev constructed. So it's formed of a bunch of terms, which I'm going to call h in plus h prop for propagation plus h out. And so what's our Hilbert space here? We should always know what Hilbert space we're working in. So our Hilbert space is, we have a bunch of qubits. Okay, I'm going to break up the qubits in my circuit because they're going to play different roles. My first qubit is going to be special. This is going to be the output qubit. This is the one I would measure at the end of my QMA verifier circuit to see if I accept or reject. I'm going to make that the first qubit just for convenience. Then I have a bunch of, okay, what does this circuit take in? It takes in a witness, right? This is the circuit for our QMA problem. So what does it take as input? It takes the witness that I'm running the verification on. So I have a number of qubits W where I feed in the witness. I have a number of qubits. Then I might need some scratch qubits, so some ancillas. Let's call those A. And then I've got my clock Hilbert space, which is not a qubit, but a t+1 dimensional Hilbert space. Okay, so that's my Hilbert space. So this qubit 1 is always going to be the output qubit. This is the witness register, where we put in the witness we got from Merlin. These are ancillas, which we're going to initialize, which should be initialized to some fixed state, for example, the 0 state, because we might need some scratch space during this computation. Okay, so then what's this Hamiltonian? So what do we want? We want this Hamiltonian to make sure that any component of the ground state with support on time 0 should be in the state that corresponds to an input to our circuit. So how do we do that? Well, we'd like to initialize this qubit. We want to be initialized to 0 as well for convenience. Initialized to 0. Okay, so we'd like to, what do we need to do? The witness could be anything. At the moment we're just going to leave that free. We want to initialize these scratch qubits, the output qubit and the ancillas to 0. So how do we do that? We need to give extra energy to states that are not 0 on these two qubits. So we can do that simply by taking the projector onto the 1 state on the first qubit. Tensor, and we only want to impose this initialization when the clock is indicating time 0. And then we want to do the same for all of the ancillas. So projector onto the 1 state. So this gives extra energy to any state where the first qubit is in the 1 state, because then it picks up some energy contribution from this. So this is just, maybe I should not write this. Maybe let's actually just write it out. So this is the projector onto 1 on the first qubit, and this is projector onto 1 on ancilla J. For now, I'm leaving completely free what the there's no condition on what the witness register can be in. That can be in any quantum state and get no energy from these terms. But the ancillas and the output qubit need to be initialized to 0. Our H prop, well, this is going to be a sum over T HT. And what's HT? H sub T. These terms look like a half identity tensor. These are the important terms in the Hamiltonian. T projector onto T plus projector onto T plus 1 is on the clock, minus a half U T plus 1 tensor T plus 1 T minus a half U T plus 1 dagger tensor T plus 1. Okay, what's going on with this Hamiltonian? Well, think about what happens if we apply this operator to a state. Look at these two terms for now. What does this term do? Well, if the clock is in the state t, it increments the clock by 1, and it applies the corresponding gate from the circuit. So this advances the clock by 1 step and advances the computation by 1 step. Okay, but this needs to be Hermitian. This is a Hamiltonian. So we need to have the Hermitian conjugate. What does this term do? Decrements the clock and evolves our computation backwards in time 1 step. That's fine. Quantum computation is reversible. We can go forwards or backwards. Okay. So this increments the clock and advances the computation 1 step. And this decrements the clock and goes compute backwards in time. Say uncomputes. What are these terms here for? Well, basically, these are, in subsets, these are here to make sure the clock ticks at all. So if you don't have these terms here, you can go away and, as an exercise, see that although you do end up with the right ground state, you also have other states in the ground state subspace, in the zero energy subspace, that don't have a clock that ticks. So these kill off, give energy to states where the clock doesn't tick. Okay, that's not. I don't have a good intuitive way of seeing that directly from here. Another way of thinking about this term, though, is that if we look at what it looks like as a matrix, let's just look at the t+1 subspace. Then what does this look like? This looks like the matrix up to constant factors. It looks like this matrix. Now imagine I have a state with amplitude alpha on this first state. Then how do I get a this is a positive semi-definite matrix, right? Its minimum eigenvalue is 0. If I've got alpha amplitude here, the only way I can get energy 0 from this is to put alpha amplitude here. So these kind of terms, this is like looking at one term here in the this is 1ht, just for some looking just in the tt+1 subspace. This term means that this forces the zero energy states to have equal amplitude across all of the components of the computational history. So if we have amplitude on the state psi t for time t equals 1, then we also have to have amplitude alpha on time on psi t for time 2, and so on all the way up to time capital T. So that's another way of thinking about seeing what's going on with these terms. And finally we want, okay, so up to now what I've got is a Hamiltonian that you can go away and prove, if you want, has a unique zero, and its spectrum is non-negative, so it has its eigenvalues are 0 or positive, and the ground state is the state I wrote down over there. The history is a history state. And the last thing I want to do, okay, we're trying to remember what we're trying to do here is to construct a Hamiltonian that. So what are we trying to do? We're trying to construct a Hamiltonian, use the only thing we know about QMA, which is a QMA problem, which is that it has this witness verification circuit, to construct a Hamiltonian such that the answer to the local Hamiltonian problem is the same as the answer to that QMA problem. So what we want is a Hamiltonian where if the answer to our original QMA problem was yes, then we have a low energy ground state. And if the answer to our original computational problem was no, we have a higher energy ground state. So how can we, at the moment the energy of this ground state doesn't depend on what the computation is. It doesn't depend on whether we accept or reject. So how can we give some extra energy in the case where this verification circuit says reject the witness? So a no instance. Well, in a no instance, we know that the circuit is going to output 0 on the output qubit with high probability. That's the definition of QMA in this case. So how can we give extra energy to that? Well, we can just put the projector onto the 0 state on my output qubit when we're in the final time state. When our clock is reading the final time, then we check if the output qubit is 0 or 1, and if it's 0 indicating reject, we give some extra energy. And this lifts the energy of no instances, but leaves the energy of yes instances alone. So now with this term means that we have different energy depending on whether the QMA problem is a yes or a no instance. Okay, we're going to prove all of this rigorously, but that's the intuition behind this Hamiltonian. there any questions? Yeah. Yeah. Yep. And we are. Okay, so what does this projector onto 1 do? This means that the 1 state has energy 1 and the 0 state has energy 0. Yeah. Think of this as an energy penalty to the things we don't want. Yeah.
Basically, the two terms in the H, the first register in two terms in HE actually acts on different. So the first one is actually initializing the output. The second one is the ancillars, right?
Yep.
Okay.
That's right. Let's go here first.
So do we need like any sort of like numerical factors to support this?
The Hamiltonian is exactly what I've written on the board there. There's one at the back. Yeah. Yes. It should be a constant. So remember, n is the number of qubits in this problem size. So that relates to I'm trying to take a QMA problem of size n. I've turned it into something with poly n, local Hamiltonian on poly n qubits, but I want k to be independent of n. Okay. Yeah.
How do we control the contribution from every part of the Hamiltonian? For example, if H out has a lot of energy cost to have a 0 on output, then it will just dominate all the other parts. And
Well, I've made
care about them.
right, but this has I've weighted this 1, 1, 1 everywhere. All of these have weight 1. So it's the interplay between these terms that's going to give us the. It's not trivial to prove. The intuition is this, but I'm just claiming that the ground state looks like the history state, and if you believe that, then what I said makes sense.
Actually, we should prove that if it's 1 on 1, then we will have
Yes, we're going to prove this rigorously. Yeah. It's not. It's it's actually the ground state of this Hamiltonian. Once I hit this, it's a low energy state, not necessarily the ground state. Okay. So I would really, to emphasize, I would really want, in the local Hamiltonian problem, I want k to be independent of n, and I want d to be independent of n. And I'm not quite achieving that because I have this clock whose Hilbert space dimension is capital T. T is the length of the circuit. That's by the definition of QMA, it's got to be, the verifier circuit has to be polynomial in n, the number of qubits. So T is poly n here, which is no good. Okay, and I'm not going to have time in this lecture to fix this up, but it's not too difficult to then take what I've done here, and if you look at the lecture notes, you'll see that that final step done of breaking this down into qubits and making everything work. Okay, good. Okay, so let's now prove, what I want to do now is to try and prove to you that the local Hamiltonian problem, that this Hamiltonian problem, this Hamiltonian actually proves QMA hardness. With this Hamiltonian, we can prove QMA hardness of the local Hamiltonian problem. So first thing I need is, first I'm going to need a technical lemma, it's not something very difficult. So, but it's going to be very useful that we can actually rewrite H prop. So by this squiggle equals, I mean this is equivalent up to a unitary conjugation. I.e., so this means i.e. H W dagger for some unitary W is equal to identity tensor E, where E is some matrix I'm about to write down. And E, what's this E? E is, if I write it out, it's sum over T, a half T minus T plus 1, T minus T plus 1. So it's really a... Okay, or if I write this out as a matrix, what does this look like? This looks like the matrix that's got a half in the top right corner. And then it's got ones down the diagonal. And minus a halves down the off diagonals. And zeros everywhere else. Okay, so this is almost a tridiagonal Toeplitz matrix. So Toeplitz matrix would have the same value down all diagonals. It's almost a Toeplitz matrix, except it doesn't have ones in the corners; it has halves. Okay, so that's so I claim that my H prop is up to a unitary conjugation, looks like identity tensor this matrix. So let's prove that. Well, the proof is not very difficult, and the proof is simply I can write down W and then verify. Just take W equal to this, and you can check that this is unitary. Right, you just need to check that W dagger W is equal to identity, and so that's the unitary that does this, where I define the first term of this. So this is t is running from 0 to capital T always. I is from 1 to little t. So what does this look like if I expand it out? This looks like identity tensor 0 on the clock plus U1 dagger tensor 1 on the clock plus U1 dagger U2 dagger tensor 2 on the clock plus all the others until you get to the final term where you have UT dagger UT minus 1 dagger, nope, other way around. Sorry, U1 dagger all the way up to UT dagger tensor T, capital T on the clock. Okay, you can just verify, conjugate this matrix by this one. You'll see that a whole load of terms cancel and you end up with exactly this thing here. Okay, I'm not going to go through that. You can do it for yourself. But intuitively, what's going on with this unitary W? What's it doing? Well, it's checking that if the time is t, then what it's doing is it's undoing, because this is U dagger in the backwards order. So if the time clock register is reading t, then what this part of the unitary does is it undoes all of the gates up to that point and it undoes it back to the initial state. And if this is t plus 1, it undoes t plus 1 steps of the computation. So that's what this unitary intuitively is doing. It's uncomputing all of the components of the history state, if you like. Good. Okay, so that lemma is going to be useful later and in a couple of places. So no, I wrote on a board that doesn't move. Damn. Okay. Okay, so what do we need to prove? We need to prove two things. We need to prove that yes instances of our QMA problem imply that this Hamiltonian I've constructed has a low ground state energy. Okay, it won't quite be 0 because we added the penalty on the, well, it won't quite be 0 necessarily, but we can give a good upper bound on the ground state energy in yes instances. And then we have to prove that no instances, we need to prove a lower bound on the ground state energy for no instances, which is higher than that. So let's do which do you think will be the easy case and which is going to be the hard case to prove? It's a decision problem. There's just a yes or no answer, and it's literally yes or no. Is it the yes instances or the no instances that are easier to prove? So who thinks the yes will be easier to prove? 1, 2. And who thinks the no will be easier to prove? It's a very mostly abstentions, but the 2 people who voted yes, you got it right. Why do we know that? Why is it kind of shouldn't surprise us that it's easier to prove the yes case? How do we prove that something has a low energy eigenstate? How the ground state energy is upper bounded by something? What's one easy way?
Just give the witness.
Yeah, or if we want to upper bound the eigenvalue of a matrix, we can just take any state we like. Variational characterization of eigenvalues. Lambda 0 of H is equal, of any matrix, is equal to the minimum over states of this. So that's certainly upper bounded by, if I take some fixed state here, As long as I have a good trial state here, I'll get a decent upper bound on the minimum eigenvalue. But what's a good trial state here? The history state. Because I constructed this Hamiltonian, the whole intuition behind this Hamiltonian is that history state is going to be a ground state, or at least, and that intuition is pretty good. And if we just compute this quantity for the history state for this Hamiltonian, we'll find that we get a pretty decent bound on the, we'll get a good enough bound on the minimum eigenvalue. So in fact what we're going to put here is the history state, which I wrote in capital phi. I should have written this as phi to avoid confusion. Okay, so let's compute that. I mean, before I do that computation, let me just note a couple of things that will make the calculation a bit easier. So the history state is, psi is my history state. Okay, but I need to say what, I want to pick a history state where the input is correctly initialized. I want it for where psi 0 is correctly initialized. So any state on the witness register that I've correctly initialized my output qubit and my ancillas to the 0 state. So that's the state I'm going to put in here. So a couple of things to note. There's a way I can rewrite this history state as W dagger psi 0 phi 0, where phi 0 is equal to one over root t plus 1 sum over t. I just take that unitary there. Okay, W uncomputed, all the components of the history state. W dagger generates them. So if you just multiply that out, you'll see that start with the initial state and the superposition over all clock states, and W dagger multiplying by W dagger transforms it into the history state. So that's going to be convenient and simplify things a bit. Note also that probability that UW outputs, we're thinking about yes instances, so the probability that we output 1, actually let's think about the probability that output 1 is high, so the probability that we reject the witness in a yes instance is low, so we know that that quantity is less than epsilon. But what is that equal to? Well, that's equal to the probability of measuring the output qubit to be in the 0 state in my final computational state. So we have a bound on this quantity. Okay, so now with that, let's compute the minimum eigenvalue. Let's compute this quantity here. So I'm going to compute, so lambda 0 of h is less than or equal to psi overlap with, well, we've got lots of terms in our Hamiltonian. Let's break it up. Psi h in, psi sum over t, psi ht psi, plus the last term I have psi h out psi. So in the interest of time, I'm going to, again, this is literally just calculations now. This term is equal to 0. We've got a correctly initialized state. Okay, we've constructed it essentially so that it picks up no energy from the input Hamiltonian, but check that if you don't believe me. This term here, well, h out is the projector onto the final clock state and 0 on the output qubit. So this is actually exactly equal to this. So we know that this is less than or equal to epsilon. If you expand it out and compute, you find that you just get this, which we know is upper bounded by epsilon. And now this term here. Well, let's do that one. Let's write that one out. So I want to calculate. Okay, let me not expand this out. Let me just do everything in one. So this is h prop. So let's compute psi h prop psi. Well, psi h prop psi, that's, well, let's rewrite our history state in this way. So our history state is, we can rewrite as psi 0, phi 0, w, dagger acting to the left, h prop, w dagger times psi 0, phi 0. Okay, that's just using this. But we know what wh prop w dagger is from that lemma. Right? It looks like identity tensor E. So this is just psi 0 identity, psi 0 times phi 0 E phi 0. What's phi 0? Well, it's just the all ones vector appropriately normalized to be length 1. And if you look at what's this all ones vector multiplied by this matrix, well, we get a half minus a half in the first component, which is, so we get a half times 1 minus a half times 1, which is 0. The next component, we get a minus a half times 1 plus 1 times 1 minus a half times 1, which is 0 as well. So all of these rows sum to 0. So if I multiply the all ones vector by this, I get 0. In other words, this is a 0, phi 0 is a 0 eigenvector of E. And you can show that this matrix is in fact positive semi-definite. So that's the minimum eigenvalue. So this is, in any case, this is equal to 0. Okay, so now we're done. We actually have a good bound on the minimum eigenvalue of yes instances. We can upper bound it by epsilon. Okay, I've made a small mistake because this term, if you expand it out, I don't get this. I get this times my normalization. So I get a 1 over t plus 1 factor. Right, because my history state, did I erase it? Yes, yes. But my history state is a superposition over all times. Each comes with amplitude root 1 over root t plus 1. So in fact, there's a t plus 1 factor here missing. Okay, so that's a pretty good bound. That's a bound that the minimum eigenvalue in yes instances is epsilon over t, order epsilon over t close to 0. Remember, t is poly n. So in fact, this eigenvalue is pretty close to 0 as n becomes large and epsilon is small. Okay, that was the easy part. So now I need to do the hard part. So the harder part is proving a bound for the no instances. And this is harder now because instead of just having to give existence of a low energy state, and I can just make a good guess, now I have to prove that for all states, even ones that don't look anything like the history state, I have a lower bound on the energy. So that's what we're going to do next. Are there any questions about at this point? Okay. No, we proved that yes instances have a low energy. We proved an upper bound on the energy of yes instances. We used the fact that we're in yes instances this. We know that the probability of outputting 0 is small, and we made use of that fact in this bound. Right? The probability of rejecting the witness for yes instances is small. The probability of accepting it is high. So the probability of rejecting it, which is this quantity, is small. Anything else? Okay, so let's prove that now, if we're in a no instance, now we need to prove that we have a good lower bound on the ground state energy. Okay, so what does the fact that we're in a no instance tell us? It tells us that for any witness, the circuit will reject it with high probability. Probability U, W, outputs 1. Sorry, the probability that outputs 0 is high. Right, with high probability, we reject. What's this? This is psi t projector onto 0 on the output qubit, the final time state. Sorry, this is just this t. And we know that this is bigger than or equal to 1 minus epsilon. So with high probability, we reject the witness, any witness that we're given here. Okay, so to prove this, I'm going to need a lemma that's generally known as Kitev's geometrical lemma, or just the geometrical lemma. For that, to state that lemma, I need one definition. I need to define what the angle between subspaces is. This is just the definition. So if I have two subspaces of a Hilbert space, let's call them L1, L2, then the angle or cosine of the angle between those two subspaces. So think of these as a, we've got two hyperplanes in Hilbert space, and we want to define what the angle between those hyperplanes is. So the angle, cosine of the angle, is defined by the maximum over states in the first subspace and states in the second subspace, 1, 2, of the overlap. So think about how I define angle between two vectors in high school maths, right? U dot v is equal to cos theta when u and v are normalized. Okay, so that's just, now we're just looking at the minimum angle, so the maximum cosine between, of any vectors in those two subspaces. Okay, so that's just a definition. And now with that I can state Kitaev's geometrical lemma. Well, but it's, fidelity, yes, it's the overlap, even it's pure states here, but it's the maximizing it over all vectors in the subspaces. And then take an inverse cosine to get the angle. So yeah, it's the maximum fidelity of states in those two subspaces. Okay, so Kitaev's, the geometrical lemma, I'm not going to prove it. If you want to see the proof, it's not particularly difficult, but in the interest of time, I'll leave the proof. The proof is there in the lecture notes in full. If we have two operators that are positive semi-definite, so in other words, these are Hermitian matrices whose minimum eigenvalue is 0 or bigger, no negative eigenvalues. And if I look at the minimum non-zero eigenvalue, and I don't have a good notation for this, minimum non-zero eigenvalue of A and lambda min non-zero of B. So this is an assumption. If we happen to know that the minimum non-zero eigenvalues of these things are lower bounded by mu, then the geometrical lemma says that all of the eigenvalues of A plus B are bigger than 2 mu sine squared theta over 2. And what's theta? It's the angle between the kernels of these operators. So theta is equal to the angle, in the sense just defined here, of the kernel of A, between the kernel of A and the kernel of B. And what's the kernel? Kernel of A, what's that? That's the span, that's all of the subspace of 0 eigenvalue eigenvectors of A. And similarly for B. So it's the angle between the 0 eigenvalue eigenspaces. Okay, so that's what the geometrical lemma says. Okay, why is this useful? So let's zoom out a moment and see where we're going. What's the problem with proving that that this Hamiltonian, giving a lower bound on the minimum eigenvalue of this Hamiltonian? Well, these terms are rather simple. These are just projectors. Right? H in and H out are projectors. They're in the standard basis, and they commute. So we know about the spectrum of those. These are just have ones and zeros. They commute, so these are easy to get a handle on. The problem is this H prop term, which is a bit more complicated, but we have a decent handle on that, right? It's actually, we know that looks like up to a unitaries conjugation, which of course doesn't change the eigenvalues. It looks like this. So we actually have a pretty good handle on the spectrum of this as well. In fact, the tridiagonal Toeplitz matrices, we actually know analytically what all of the eigenvalues and eigenvectors of this matrix are. So what's the problem then? We know about the spectrum of all of the parts of components of this Hamiltonian. The problem is that H prop doesn't commute with H in and H out. Right? And when we have a sum of two non-commuting operators, how the spectrum changes is not so trivial. What the geometrical lemma gives us is a way of, if we know we have a good handle on the spectrum of A and the spectrum of B, then it gives us a way of getting a handle on the spectrum of A plus B. So now you can hopefully see how we're going to apply this lemma. We're going to take A to be H in and H plus H out. Right. And we're going to take B to be equal to H prop. And then we're going to use our knowledge of the spectrum of these two parts of the Hamiltonian to say something about the spectrum of the whole Hamiltonian. Yeah.
What does it mean B plus B is greater or equal to?
All of the eigenvalues of A plus B are lower bounded by this. Okay. These are Hermitian matrices, so the eigenvalues are real, so this is meaningful. Is there any other questions? Okay. So, what do we need to do in order to apply the geometrical lemma? Well, we need to know or have a bound at least on what the minimum non-zero eigenvalue of A is, what the minimum non-zero eigenvalue of B is, and we need to know what the angle between, or have some handle on what the angle between the kernels is. Okay, and then that gives us a value for mu we can put in here and a value for theta we can put in here. Okay, so that's what we need to figure out. One bounds on lambda minimum min non-zero of A and of B, and on theta between kernel of A. So this is what we need in order to be able to apply the geometrical lemma usefully. Yeah.
Do we need the value of this mu? I mean, we already know that they exist, so basically we can know that X is a beta. So we didn't finish already the...
Nope. Because remember that, and where's the local Hamiltonian problem there? We need not just any old bound, we need to make sure that beta is bigger than the bound we just derived, the alpha we just derived. So we've got alpha as epsilon over t plus 1. We better make sure that beta is bigger than this. In fact, bigger than this by something that's 1 over a polynomial. But thanks for asking that. That's a good question. Okay, so I'm going to claim, some of these are very easy. So I claim that the lambda minimum non-zero of A, right, H in plus H out, I claim that this is bigger than or equal to 1. Let's use NZ. And can anyone see why? Yep, sum of two projectors that commute. There are all of the eigenvalues are 1 and 0 of each of those. When I add them up, I just get integer eigenvalues. And I'm taking the minimum non-zero integer, positive integer, which is 1. So that's easy. I claim that same thing, minimum non-zero eigenvalue of B is, I claim that this is asymptotically lower bounded by 1 over t squared. Okay. How do I prove this? Remember, B here is H prop. And we know, so we proved that, or at least I claimed and left you to verify that B is up to a unitary conjugation, let's write it the other way around, is equal to this identity tensor, this E matrix, this tridiagonal Toeplitz matrix. So identity tensor something just means I multiply up the degeneracy of the eigenvalues without changing them. So I get the same eigenvalues with additional degeneracies. So really what we need to know is we need to know the eigenvalues of E. And these happen to be very well known. These are, you can derive these analytically because this matrix has a very special form that's been extremely well studied. Crops up all over physics. And okay, I'm not even going to derive these. I'm just going to claim that these are already known. And in fact, I'm going to give you enough to go away and verify it, but this is just kind of black magic. I'm just going to tell you what the eigenvalues and the eigenvectors are, and you can, of course, then just check that put them in the eigenvalue equation and verify. How you actually derive these eigenvectors is rather interesting mathematically, but I have no time to talk about it. So in terms of proving things, this is fine. You can just go away and now check. So up to normalization, the eigenvectors look like sum over j, 0 to t, cosine qk, j plus a half, j, and qk values of E, and eigenvectors of E are this, and then qk is just integer multiples of pi on t plus 1, where k goes from 0 up to t. Okay, that's just the fact that the eigenvalues of this matrix, one can derive these. That's what they are. You can plug these things in the eigenvalue equation and check that I'm not lying. And then the minimum what's the minimum non-zero eigenvalue? So k equals 0 gives me eigenvalue 0. K equals 1 gives me the smallest non-zero eigenvalue. And if I plug that in here, I have a cosine that goes as 1 over t squared, or 1 minus 1 over t squared. And then we end up with something that's going as 1 over t squared. We actually know the eigenvalue exactly. I just don't need that. I just need that it goes as 1 over t squared. That's all I'm going to need. Okay, so you can go away and check that. So now let's see how we're doing for time. I think we're okay. Okay, so now the harder part is getting a handle on this angle between the kernels. So let's see, because I want to leave some time at the end for if you've dropped off, I'm just following this and it's now I'm just writing math on the board that you need to go away and read for yourself later and digest. So in the interest of, I would like to, at the end, to talk a bit about what this result actually means for physics. So I may at some point, in the interest of time, just start claiming things and referring to the lecture notes for the proofs. But let's see how far we can get. So claim that this thing I'm trying to bound, I claim that this is asymptotically lower bounded by 1 minus root epsilon. Epsilon is this epsilon over t plus 1. So let's try and prove this. Okay. Let's think about what the kernel of A looks like. A is the initialization Hamiltonian plus the output penalty Hamiltonian. So what does the 0 eigenvalue eigenstates of this look like? Well, so remember, this is h in plus h out. So they should be correctly initialized. If we're going to have if we have any support on the on time 0, then h in means that to have 0 to pick up no energy penalties, we better have a correctly initialized state. So if we have something on time 0, we need to have correctly the input and the ancilla qubits to be correctly initialized. So that's in the kernel for sure. Sorry, the projector here. So this is 0 on the clock. What about if we have time? The clock is reading time t for some t that's between not the final state or that's somewhere in the middle of the computation. Well, then we don't, essentially there's not really any constraints on what the Hamiltonian from h in and h out. These only look at the initial and final states. So anything goes there. And then something interesting happens with the final state. So if we've got the final time state, capital T, well, to have a 0 energy eigenstate, we have to pick up no energy from h in and h out. H in doesn't see this. It only looks at the time 0 part. So we need to have h out not rejecting the witness. So that means we need to accept the witness. In other words, we need to have a 1 on the output qubit and then any other state on the rest. Keep writing 10. Okay, so if you think a bit about that. That, in fact, is the kernel of A. And in fact, I've now exhausted. That's all of that spans the entire subspace. There's nothing else I can add to that set and have for zero. That gives me 0 energy. Okay, so now I can write down the projector onto that kernel. So let's take pi A is the projector onto this subspace, right? So that's the sum over phi, where I sum over phi in this set here. Equals, so this is the projector onto the kernel of A. And if I conjugate A by this W matrix, then this is just a calculation, so I'm going to skip the details, but just tell you what comes out. I have a projector onto 0, zeros on the ancillas, tensor 0 on the clock. Plus sum over t, 0 smaller than t smaller than capital T, identity tensor t, plus u dagger, right, 1 tensor identity, just 1 on the output Cubitt u. So this is really literally just multiplying w by the sum of the states in this set and just writing out what you get out. Nothing interesting. I'm doing this because I want to then give a short name to this. I want to call this thing. This is a projector. I want to call it pi I. This is a projector, and I want to call it pi f for initial and final. Okay, so let's at least, now I want to compute this angle. Let's compute cosine squared of theta. So what's the definition? Max. I have to take the maximum of overlap of vectors in the kernel of my two subspaces. So this should be in kernel of A. Eta should be in the kernel of B. Then maximum overlap, and I've just squared both sides in the definition of the angle. Now I'm going to simplify this. Well, no, I'm not. I'm going to gratuitously insert a projector onto the kernel of A into here. Which does absolutely nothing. Because psi was in the kernel of A, so if I project psi onto the kernel of A, I just get psi back. So I've done nothing here at all. But this lets me rewrite this as max eta. I'm going to stop writing eta in kernel of B. Eta will always be in B. Psi will always be in A. Okay, I get that equality. This is by Cauchy-Schwarz inequality. Normally in Cauchy-Schwarz I would get an inequality, but I can actually saturate the Cauchy-Schwarz inequality in this case and get an equality. Okay, why have I done this? Now I'm going to conjugate by this unitary W that's been cropping up all over the place. So now sorry. No, that's fine. So but now eta, let's call this eta primed, eta primed has to be in the kernel not of B anymore, but of WB W dagger. Okay, so I've just rotated, changed basis by W. Now let's expand this out. I know what the kernel, I know what W pi A W dagger looks like. We worked it out earlier. Okay, in that basis, pi A takes a nice form. It looks like, so we now have the overlap of eta primed with my input projector, 0 on the clock. So this is a projector that gives a high energy penalty to things that aren't correctly initialized. My output or final time projector, which gives extra energy to things that are where the witness is accepted. And now we also know what the kernel of WB W dagger looks like. We know what the kernel looks like. We wrote it down over. We know what the kernel, of this looks like, because this is a rather simple thing, right? Kernel here is correctly initialized states or non-rejecting, rejecting output states or anything in intermediate time states. So actually, if we were just writing down what the states eta primed have to look like, we have that this is maximum over, what freedom do we have? We have, they look like this. Our pi in plus pi f projector. And that's equal to max over this states on the computational register pi in plus pi f phi plus t minus 1, because in this I have all of this part that doesn't care what the state on the computational register is, so I pick up a bunch of I pick up t minus 1 from here, and then the other two terms are coming from pi n pi f. Okay, but now let me rewrite this. I have 1 over t plus 1 max over phi. Let me just rewrite this in terms of the orthogonal complement. Right, so this is just 1 minus this. That's where the 2i comes from, pi f. So I'm just rewriting. And then I have this t minus 1 over t plus 1 contribution. I'm trying to bound here the minimum eigenvalue. Well, the maximum eigenvalue of minus pi I plus pi f perp, which is the same thing as trying to bound the minimum eigenvalue of pi I perp plus pi f. But we have a very good lemma for bounding minimum eigenvalues of the sum of two matrices. It's the geometrical lemma. So we can now use the geometrical lemma a second time to bound this term. So this is now, so the geometrical lemma then, from here we can, gives us that this is 2 minus 2 sine squared but now it's a new angle, t plus 1, plus t minus 1 over t plus 1. This is the geometrical lemma applied to pi I perp pi f perp. Okay. At this point, we now need to get a handle on... So the spectrum of these two is easy. These are projectors, but they don't commute because one of them is rotated by w. Now we have to get a handle on the angle between these subspaces. Okay. This is at the point where I'm now just going to claim the result and not go through the algebra. It looks similar to what I've just done here. Things are now simpler because these two operators are now simpler. We have a handle on what the kernels of these two operators look like. Because pi in, the kernel is correctly initialized initial state, and pi f, we know what the kernel looks like there. It's things that don't pick up energy from the output penalty. So now these are, we're applying a geometrical lemma a second time, but now to operators where we have a much better handle on what the kernels look like. And this we would actually, just by simple algebra, we can get the angle here. Okay, so if you want to see that derivation, go look at the lecture notes that are on, I already uploaded them, they're online. So apologies that I didn't have time to go through that, but I suspect no one's going to cry about it. Okay. I just have time to finish. So I claim that, and I'm not going to prove this, that the sine squared I claim that cosine squared of this of curly theta is less than or equal to epsilon. So the angle between these subspaces is related to what's the probability of starting with a correctly initialized state and then time evolving it all the way to something that's accepted. But we're in a no instance. We know that probability is low. It's less than or equal to epsilon. And that's in the intuition. I mean, and when you do this calculation, you see directly that that's where that's coming from. Okay. So with that, I can now put together everything that I've proven. So I have a bound on the minimum non-zero eigenvalue of A, the minimum non-zero eigenvalue of B. And if I plug this bound on curly theta into this bound on theta, which is the one I want to get a handle on, then I get that gives me that. It's just simple trigonometry, or trig identities. I have that gives me that sine squared theta over 2, the actual angle I wanted to bound, is bigger than or equal to 1 minus root epsilon over, that gives me the bound that I claimed for t plus 1. Okay, so plug the bounds on lambda minimum non-zero of A and B, and bound on sine squared theta over 2 into Kitti's geometrical lemma, and we have that h, which is h in plus h out, that's my A part, plus h prop. Plugging these values in to that expression here, I have that this is lower bounded by, well, I actually don't care about the constants. Right? This is lower bounded by 1 minus root epsilon over t cubed. Literally just from plugging in the expressions into there and doing some simple trigonometry. So what have we proven? We have a bound on yes instances we proved that lambda the minimum eigenvalue of this is less than or equal to epsilon over t plus 1. Let's choose alpha to be equal to that. For no instances, we've just proved, or mostly proved, that the minimum eigenvalue of h is bigger than or equal to something that scales as 1 minus root epsilon over t cubed. Let's take that equal to beta. Now remember, we need beta minus alpha to be something that goes as 1 over a polynomial. Right. At the moment, this looks smaller than this, right? Because I have 1 over t here and 1 over t cubed here. But epsilon, I'm free to choose to be any 1 over polynomial by QMA amplification. So I'm going to choose epsilon now, and remember this does not change the class of problems in QMA. I can freely choose epsilon to be anything that goes as 1 over a polynomial, and I get the same complexity class. If I choose epsilon to scale as 1 over t squared, then that gives me that beta minus alpha. I get that this is beta is bigger than alpha by 1 over t cubed. So remember, yes instances, we proved that they have an energy, ground state energy lower than alpha. No instances will have a ground state energy bigger than beta. And these values are separated by something that's 1 over a polynomial in my problem size. So like this, I've just completed the construction of a reduction from any QMA problem to an instance of the local Hamiltonian problem where the answer is the same as my original QMA problem. In other words, I've just proven the hardness, QMA hardness of the local Hamiltonian problem. Okay, I'm basically out of time. Let me just say a few words about what do we learn from this in terms of the physics. So remember, this means that estimating ground state energies of quantum Hamiltonian, many-body Hamiltonians, is a problem that we don't even expect to be able to solve efficiently on a quantum computer, let alone a classical one. What is this? Okay, so that tells us something about if we're doing numerics on many-body Hamiltonians. It tells us that it's going to be, we can expect it to be hard, at least sometimes. This matches up with experience, right? But this also tells us something about the physics. If we appeal, because of the Church-Turing thesis, or the quantum Church-Turing thesis, the strong Church-Turing thesis. Because here's one way of, this is a physical system, right? We could imagine, and these days it's not so unrealistic, to imagine building this Hamiltonian in the lab, in superconducting circuits, or in ion traps, or in optical lattices, or whatever. And then just cool it down until it's in its ground state and measure its energy. The energy isn't observable, right? And this is even a local Hamiltonian, so even it's just made up of local observables. And like that, can't I just find out what the energy is by measuring it? Well, it's that process of construct a Hamiltonian and then cool it down to its ground state and measure. Well, it's a very strange one, but it's a perfectly reasonable model of computation, right? In fact, it is a model of computation that's its polynomial overhead is equivalent to quantum Turing machines, or the quantum circuit model. Why? Because Hamiltonian simulation algorithm tells us that we can simulate quantum dynamics on a quantum computer, and this construction essentially gives us a way of turning any problem into any decision problem. We can turn that computation into a question about ground state energies. So in fact, although it's a weird one, it's a perfectly reasonable model of computation. It's reasonable because we could do it in the lab. It's reasonable because it's actually provably equivalent to quantum Turing machines. But this QMA hardness result for this says that, okay, if we do that, we run the computation in that weird model, that cool things down and measure model, then we'll be solving QMA hard problems. And if we believe the Church-Turing thesis that all models of computation, and including ones in the real world, are equivalent to quantum Turing machines, we've just proven that that can't be possible. That isn't possible unless PQP is equal to QMA, but let's assume that that's not true. So how do we reconcile the Church-Turing thesis and this result? Well, it must take exponentially long to cool into the ground state of these systems. It's the only possible answer, a way out of this, the only way we don't have a contradiction. Okay, so and what are systems that take exponentially long to relax to their ground state? Well, these are systems that are known in condensed matter physics. These things, quantum spin glasses are characterized by this kind of behavior. But with the quantum spin glass models you write down in condensed matter physics, it's typically extremely hard to prove that the relaxation time is exponential. Here, coming from a completely different angle of complexity theory, we have a much more artificial Hamiltonian, but we actually have a proof that the relaxation time has to be exponential. So we've gained a new insight onto the physics here from coming from a complexity theory angle. It gives us a new way of approaching that type of physics. That sort of tells us nothing new in the sense that spin glasses were already known to exist, but a whole sequence of results since Kitayev's 2000 result. Turns out in the end, when you work it out, if you make the clock local, this gives you 5 local interactions, so 5 body interactions. But a whole sequence of results culminated in that proved QMA hardness for ever simpler Hamiltonians. First 3 body interactions, then 2 body interactions, then nearest neighbor interactions on a 2D square lattice of qubits. So those results by Kitaev, Kempe, Regev, Oliveira, Terhal. And then, okay, we were at 2D lattices of qubits. That's already relatively simple systems. But okay, 2D physics is hard. That's where you have high superconductivity and complicated things in topological order. 1D is simple, right? And physicists, as far as I understand, didn't expect that you could have spin glass-like behavior in 1D. Next step was Aharonov, Gottesman, Irani, and Kempe, who proved that QMA hardness for a 1D chain, spin chain. Okay. Same kind of idea with some extra, mathematical ideas and very nice extra things that I don't have time to tell you about. And that was in some sense telling something new. We could have spin glass-like physics in 1D as well. And there, the complexity theory actually gave us some new insight into the physics. Okay, so with that, I'm going to end here. Next lecture, I'm going to try and do something similar, but in much less rigor, about giving you an insight into how computability theory can also teach us things about surprising things about the physics of many-body quantum systems. Okay, and that will be on Friday. That will be lighter than this lecture, and I won't prove things there. I'll just sketch things. Thanks.